Okay, folks. Now, in this video, I'm going to explain to you a few concepts. Okay. Um, first of all, maybe what we'll do is equilibrium expression. Okay, we did that in last class, but I just want to go through this again. Equilibrium expression. And then we want to look at reaction quotient. Okay, reaction quotient, or is it QOU? Maybe it's QUO. Okay. I always get confused here. QUO quotient? Nah, I don't think so. Okay, we'll come back to that in a minute. So reaction quotient, we're going to be looking at what are we going to be looking at? How writing an equation can change the k value. Okay, and then we'll be also looking at things like homogeneous and heterogeneous equilibrium. So these are the things that we'll be looking at. Maybe we look at other things as well, but generally this is what we're going to be looking at. Okay, so I have done this with you in class, and this is just a revision. Okay, so here we go. So let's say we have a hypothetical equation. All right, let's say we have A plus B, reversible arrow, and then we have C plus D. Okay, so let's put some numbers here. Let's say we put a 2 here. Let's say this is 1, then we put a 2 here, and then let's say we put a 3 here. Okay, and let's make this all aqueous. Okay, make all of this aqueous to make things easier. Now, when all of the states, right, when all of the states are the same, okay, they're all the same. So this is an example of a homogeneous equilibrium. Okay, after this I'm just going to write it as EQ, easier. Okay, equilibrium, homogeneous. So if it's all liquid, or gas, or solid, we call this homogeneous. If one of the states is different, then it becomes heterogeneous. Like for example, if it's aqueous, solid, or gas, aqueous, liquid, it's heterogeneous already. Okay, so I hope you know that. Now, when we have an equation like this, right, we're going to introduce something else. Let's say we put a delta H value here, and let's say the delta H value at the front here is negative X. Okay, so which means that the forward reaction is exothermic. If the forward reaction is exothermic, and I want all of you all to know that the reverse reaction will be positive X, that means it's going to be endothermic. Right, the same value X, but it's just that the forward is exo, then the reverse is endo. If the forward is endo, then the reverse is exo. Okay, so I want you all to know that. So for this equation, right, if we want to write the equilibrium expression, let's say we want to write the equilibrium expression, Kc. Kc is what is in our syllabus. C stands for concentration. Okay, there is something called Kp as well. P is pressure. But we don't do this in our program. We don't do this in Muffy. So this one is not in our syllabus. So we don't deal with pressure. We only deal with concentrations. So for the equilibrium expression, how we will write it is we take the products, concentration of C, power of 2, concentration of D, power of 3. I hope you know where I'm getting the 2 and the 3 from. It's from the equation itself. Then concentration of A, power of 2, and the concentration of B, power of 1. This is the equilibrium expression. So this is what we call the equilibrium expression. Okay, equilibrium expression. Now, let's say the value is let's say the value is 400. Okay, the value is 400. What is the unit? Let's work out the unit here. So the top is molar squared times molar cube. The bottom is molar squared times molar, right? So if you can see, you will notice that this and this will cancel off. This will cancel off completely, and there will be left an m. So this will be m, 400 m. Let's say this value is at let's say 600 degrees Celsius. So at this point, I want to tell you these values, right? This equilibrium constant. This is called an equilibrium constant. This value is called equilibrium constant. So whenever a system achieves equilibrium, it will have a value, right? And this value is temperature dependent. If the temperature changes, that value will change. We will probably talk about this later. So this is equilibrium constant. It is calculated at using the concentrations at equilibrium. So only when the system is at equilibrium, we use the values and we get an equilibrium constant. All right. And it's temperature dependent. At different temperatures, it will be different. Okay. So if the value is 400, then we know the system is at equilibrium. If the value is bigger or smaller, then we know the system is not at equilibrium. Okay. So for example, let's say we have a container. Okay, let's say we have a container, and inside of this container we put A and we put B and we allow it to react. Okay, so we set the temperature to be 600 degrees Celsius and we allow this value to this reaction to proceed. Okay, after a while, maybe after a few minutes or maybe after a few hours, you realize there is A and there is B and then C and then D. Okay, so this reaction, the products were C and D. So what you do is at that moment, you take some A out, measure the concentration, take some B out, measure the concentration, take some C and D and measure their concentrations. So you take the concentrations, let's say time is, let's say 1 hour. After 1 hour, you take all of the concentrations and then you use the same formula. Concentration of C power of 2, concentration of D power of 3, divided with the concentration of A power of 2 multiplied by B. You take all of this and you get a value. Let's say the value is, the value that you get is, let's say 150, okay, M, because the unit is M, no? Then what you do is you come back after maybe 3 hours. You come back after 3 hours and you do the same measurement. You take some A out, you take some B out, and then C and D, and you put them into the formula, and you get a value which is, like, say 400 M. Then you come back after 10 hours. Let's say you come back after 10 hours, right? After 10 hours, you come back and you measure again, the value is still 400. Okay, all right. Then something happened. Let's say there was a power cut. Okay, there was a power cut, something happened, and then you come back and let's say time was 15 hours and there was a power cut. That means suddenly there was no electricity, and you come back and then you notice the value has now become 80. Okay, become 80. Okay, so last one. Then you make some changes, you did something, and then you come back, let's say 48 hours, 2 days later, and then you realize now the value is 1500 M. Wow, the value has really changed. Okay, so what I want to tell you is, if you look at this equation just now, right, we look at the original equation here, I wanted to notice when the system is at equilibrium, the value is 400. So I can tell you at this time, these two times, the system was at equilibrium. System was at equilibrium. Okay, the system was at equilibrium. That means the value is 400. This one, the system is not at equilibrium. This one, system is not at equilibrium. System not at equilibrium. System not at equilibrium. Both of this not at equilibrium. So these values, right, so this one we call K. So K, this is K. This we don't call K, we call it Q. we call this Q. So whenever the value is not the same as the equilibrium constant, we call this Q. Q is called reaction quotient. This is Q. Okay, reaction quotient. The formula for equilibrium constant and reaction quotient is exactly the same. Only if the system is at equilibrium, we use the symbol K. But if the system is not at equilibrium, then we use the symbol Q. Okay, I hope you understand that. Now, you see, like the original equation here, right? Okay, so the original equation here was 2a. Okay, what I'm going to do is I'm going to try to copy this. I'm not very good at this kind of things. I'm still learning. So I'm going to copy this. I'm now going to bring it down here. I'm going to bring it down here. Okay, let's say I bring it down here. Okay, so that's the equation. Okay, so what we're going to do is, let's say lah, in the exam or under whatever circumstances, you're given an equation. The equation is 4a plus 2b. You get 4c and then 6d. I hope you can see what just happened here, right? What happened here was the equation has been multiplied by 2. For whatever reason, maybe the student made a mistake, or the examiner is just trying to be cheeky. They have multiplied the equation. So if you write the k for this expression, it will be c power of 4 and d power of 6 divided with a power of 4 and then b power of 2. Okay, and then, right, if you compare it with the original equation here, let's say compare it with this. Okay, let's steal this equation away. Let's steal this equation away from here. Oops. Okay, let's steal this equation away from here. Let's bring it here. Okay, let's bring it. Bring it. Okay, let's bring it here. Okay, now I want you to look at this equation here. Do you see something? Okay. Do you see something? Let me try to erase the unnecessary parts here. Okay, erase. Let's clean this up a little bit. Clean. Okay, bear with me for a while. And let's do this again. Okay. Do you see what I see? At the moment, I don't see anything. Okay, let's say KC. Okay. Now, do you see this? Do you notice that if I decided to put a 2 over here, right, it will become this. Do you notice that? Mathematically, it will become that. All right. So this K prime here is actually what? So K prime is actually K power of 2. You see that? All right. So if this is K and this is K prime is actually K power of 2. That's what it is. So if an equation is given to you and it's been multiplied by 2, with 2, what you do is you take the original K value, which in this case was 400, right? It was 400, and you just power it with 2. That's it. That will be the value. So it all depends on how the equation is presented to you. Let's say the equation presented to you was, okay, I'm going to try to copy this again. It was a plus half b and then c plus 3 over 2d. Okay, let's say equation is given to you like this. So you notice the original equation has been divided by 2. So if I write the k expression here, let's say k double prime. If I write the k expression, it's going to be c power and then d power of 3 over 2, then concentration of a, and then the concentration of b power of half. That's what I'm going to get, correct? So if you observe this with the original equation, which was this equation, you observe it with this equation, right? What we have actually done is we have taken this original equation and then we have actually square rooted the whole thing. We square root the whole thing. When we square root this equation, what you'll end up getting is actually something that looks like this. Okay, c power of 2, d power of 3 divided with a power of 2 b, and then you are square rooting it, so times half. So if you times half, right, if I just do this, c 2 times half, then here was d 3 power of 2, okay, 3 times half, okay, sorry, let me just make it easier for you to see. 3 times 1 over 2, and then over here it is a 2 times half, and then here was b with half. So you see the equation looks like that, correct? So k double prime is actually square root of k. So which means that it was square root of 400. This one I know lah. This is going to be 20. Okay. So that's what it is. So it all depends on how an equation is presented to you. Okay. It depends on how an equation is presented to you. So if the equation has been doubled up, that means you square the k. If the equation has been halved, then you square root the k. Right? Easy. So that was what I was trying to tell you here, is how to write an equation, that how we write an equation can change the k value. K value only is dependent on temperature. That's it, nothing else. Is only dependent on temperature. It's not dependent on anything else. So last part here, homogeneous and heterogeneous equations. Okay. So you see, when we write homogeneous equations, right? I hope I can remember the original equation is not. So let's say a plus b, this was 2, and then it was 2c plus 3d, correct? Okay, so initially I told you this was all aqueous. Okay, if this was aqueous, okay, or it was like this. Okay, let's say it was liquid, and liquid, or it was like this, gas, and gas. Let's say they were all like this, like homogeneous. Okay, they're all homogeneous. Then the expression will be the same for all of them, which will be c power of 2, d power of 3, a power of 2, and b. Okay, that's what it will be. Got it? All right. So that will be how we write the expression for all of this, because they're all homogeneous equilibrium. If there was such a thing like this, let's say there was like 2a, and let's say this was okay, let's make it simple. Okay, 2a, and this was aqueous, and let's say this was b. Bad idea. Let's say this was b, but this was solid. Okay, and then this is 2c, and let's say this is aqueous, and this is 3d, this is aqueous. So under these circumstances, we never ever under any circumstances include solids. Solids are never included in k expression. Never ever, even if it's homogeneous. Okay, even if you're homogeneous. So like for example, let's say it was 2a solid plus b solid, double arrow, 2c solid, and then 3d solid. Okay, let's say it was like this. It's never ever included in the expression. So for this one, for this one just now, okay, so the expression will be like this. It'll be let's say it'll be c squared, and then d power of 3 divided with a power of 2. That's it. That will be the expression for this one. Okay, we do not include solids into the expression. So as far as our syllabus is concerned, it's always aqueous lah. It's always aqueous. It's never liquid or solid or gases. But just to let you know, you will never get a situation where you'll be aqueous and let's say somebody is aqueous and somebody else is gas. You won't get a situation like that. It's either everybody's aqueous or everybody's liquid or everybody's gas. Easy. All right. So as far as our syllabus is concerned, we are only dealing with KC, which is concentration. So it's going to be mainly for aqueous species. So one more thing, let's say if you had a situation like this, if this was aqueous, okay, and let's say B, this was liquid, and let's say 2C, for whatever reason this is also liquid, and this is 3D, and this is aqueous. So this is a heterogeneous equilibrium, right? Heterogeneous because the states are not the same. So when you write the K expression, you only include the aqueous. You do not ever include the liquids or solids or gases. Okay, so it's going to be like this. Ta-da, then done. All right, people. So that's what I wanted to do with you today, and this is what I did with you in class the other time, and here we go. All right.